Hey. Hello, everyone. This is another episode of Weekly Live Contracts, and today we're gonna discuss Rainbow Bridge, especially the contracts on the near side and the way we verify Ethereum blocks, and also take a look at the prover, which is how we prove that some event exists on Ethereum side using proof from the client on your side. Okay, let me present. Cool. So this is Rainbow Bridge, and it's split into contracts. You have ETH and near Ethereum. It's a Ethereum contracts. Near is a contract on near side, and it's split into multiple contracts. So one of them Ethereum client. So this one proves, this one reconstructs canonical chain using light like block headers from Ethereum, and it verifies proof of work to find the canonical chain. Next is ETHProver. ETHProver is a contract that takes a proof, a block height, and verifies that this block is present, and it's a part of the canonical chain. And ETHTypes is a utility that's shared both by ETHClient and ETHProver. There's also a mintable fungible token, but we'll probably not have enough time today to review this. But it allows to mint tokens when they are locked on the Ethereum side. So let's actually take a look at what's going on Ethereum client first. So Ethereum client contract. Yeah, go ahead.
I'm just curious from like a really high level. So this is like ETH client, and there's probably a near client that's like a light client. Like how would you quickly explain like what is like light client?
Yes, good question. So light client is some kind of program that tracks a blockchain. So it allows you to verify that a given block is part of the blockchain and it's part of the canonical blockchain. So for proof of work system, it actually verifies the proof of work, which is fairly simple. You just need to compute the hash of the header that is given to you, and then verify that this hash is has enough zeros in front of it, and this is the power of work. And then on Ethereum, for near light client, you need to verify signatures and reconstruct the chain using a proper transition. So basically, there's a fast path that allows you to skip entire epochs, I assume, and there's a short path that allows you to skip from the beginning of the epoch to the given header. And all you need to do is to know who validators are from the previous epochs, and so who are active validators for the given epoch, and then verify their signatures to make sure that the signature matches on the header. That way you prove that enough stake validated this given transition. So we cannot really do this on Ethereum because it costs too much gas right now. So instead we rely on challenges. So that's a optimistic approach. So we post a block, then the block is backed by enough stake, then anyone can challenge this block by providing an invalid proof, or like indicating which signature is invalid. And if you prove it, then you keep the stake and the block is reverted. So the plan is to switch for pessimistic bridge or like actual real bridge where all signatures are verified, and we may need to switch our curve for validation and provide some extra record in the block so you can actually validate it on every header, so you don't need to do challenges. That will allow you to have like super fast finality on Ethereum, so you don't need to wait for challenges and like don't need to care about challenges. Does it make sense? Cool. So the client is essentially keeps track of previous canonical block header hashes. So they stored in a map by height, in this case block number from Ethereum towards the hash of the block. We use types from Ethereum. They are slightly re-implemented to implement board serialization. So now, if you want to know what's the block header at the given height, you can query it. We look at the canonical header hashes at the given height. We find the block header hash. Then you can look up the block header hash and get the block header. There's some extra stuff that needed to upgrade, and there are some initialized stuff that are needed to verify the is hash. So is hash was designed to be somewhat ASIC resistant. So they designed some DAG that you need to create, which takes space. And we cannot really store like 2 gigs of
DAG is like directed acyclical graph, right?
Yeah, so I don't know exact details of how like Ethereum is hash DAG is constructed or what it is. I just know that occasionally you need to look up at some place in this DAG. It's kind of like a memory aspect of proof of work, and use this value to compute is hash.
For anyone listening in who hasn't heard of a DAG or a directed acyclic graph, my mental model is it's like a JavaScript object, but none of the keys anywhere within it can like reference something higher up in it. That would be cyclic. So it's acyclic.
Right. Yeah, so
just wanted to throw that in there for any newbies.
Cool. The main point why we need it is to be able to compute is hash for a given Ethereum epoch efficiently. So instead of actually having this object, we have something like 512 pre-computed merkle roots of the DAGs that we use. Then we can prove that at this position in this offset, value is present given a proof to the Merkle root. So this is computed once and given to the contract at the initialization time. Now, if you need to compute eth hash for a given epoch, you also provide a proof that at a given epoch, at this position, there is a certain value. Then if you go up on the Merkle tree and verify, or like compute the hashes, you should reach a root that we have here. And that's how Merkle proofs and Merkle trees work. And concept of the Merkle proof is very widely used in the blockchains because it allows you to compress set of information without having entire state and prove that this set of information is present in the trie at a given position if you only need to provide a logarithmic number of records. So you need to like just go up the tree until you reach the root. And the way you do this is you have for every node in a trie, you provide a missing value. So let's say you started from some position, then you need to know what was the missing pair on the right, a hash of this missing pair on the right. Then you can compute a parent hash by concatenating them and hashing again. Then you need to provide another missing sibling hash and so on until you reach the root. And the reason why this cannot be faked is because of entropy of the hashes. It's very low probability to have a collision, which is somewhat unrealistic to find in our lifetime without having quantum computers. So that's why we consider Merkle proofs secure. At the same time, Ethereum uses H128, which is somewhat lower entropy, and potentially, eventually someone will find it with just existing computers than 256. But when it happens, we'll see maybe like a one collision, which is not really gonna break any proof of work consensus. And if you want to try to find a match for a given object, not just like a single collision, then it's even harder because now you need to, your size of search increases. Anyway, so this is a background for how some of this works. Let's look at the contract itself. So here's the initialization. And the first thing you would notice that you haven't seen before probably is Serializer Boards. So what is Serializer Boards? It's basically a feature of a near SDK to say that this this argument has to be serialized with Boards. But because you cannot really mix JSON and Boards in a single set of arguments, they all need to be the same. Default serializer is JSON. So you need to mark every single argument with Serializer Boards right now in order for this to work. So what happens is init, instead of taking a JSON record, it kind of constructs a structure of all these arguments as fields of the structure, and then it deserializes the structure using Boards.
Why is this important? Like, why not use JSON for the initializer? Seems like it would save some hassle, and it's only a one-time call. So is it worth optimizing?
I assume it's a first header that is like fairly large. And
so it would be potentially beyond the
not
what you
really.
can do
Like
in one block.
you would
if
be
you're-
able to use base 64, for example, for this one. But you still, like, if you have to support Borscht anyway, so like it's not a big deal if you do this for one argument or for multiple. Plus, this is more efficient and like
I understand that,
init
like the
probably not
block,
an issue.
the gas that you're using is way less and the like time it takes. But for optimizing one, like init seems like the least useful thing to optimize to me, given that you
I
call it
assume
literally once.
I assume this entire contract is using Borscht for everything, so that's why.
So it's just easier to be consistent. Okay.
Right. So it's kind of like a Borscht contract. And Borscht is our serializer, and this is a binary serializer that is super efficient and fast, but it requires a schema to serialize, deserialize. So it checks that it's not initialized, and instead it calls a static variable. So this, I assume, the first time we actually see a static call, which is kind of cool. We know that it now works without having to look into. So static does not deserialize the state. It does not require for state to exist, but you can access object internally. So potentially static can be used for migrations, or it can be used for something else. Like maybe you only need to access a single element, like from an ordered map, so you don't really need to deserialize a state if you can reconstruct a prefix for an ordered map.
What makes it
And
static?
it will be more efficient. It doesn't have underscore self or underscore mute self.
Oh, cool.
So you can see another Borscht serializer. So this is the result. So result serializer tells you what type the object will be. And in this case, it or like which serializer to use when you serialize the type. So in this case, serializer is more like a deserializer. So, but to be consistent, it always use serializer. So you can call this object and it will return something like 1 or 0 in bytes. A single byte that is either 0 or 1, not a character, but actual value. All right, so let's go back to the initialization. So first thing we do, we use RLPD code. So this is coming from a library not specifically written by this contract, but it's just a standard Ethereum client library. I assume it's written by Parity. And it allows to deserialize, serialize objects. So in this case, it implements what is this? Serialize. It's a third. Interesting. Okay. Okay. There's probably impl RLP encodable and RLP decodable for block headers, and this is how it's deserialized from RLP encoding. RLP encoding, I think Mike can give you a quick explanation what is RLP.
Yeah, I mean, I just know it's recursive length prefix, but it's also similar to Borscht, where you do need. Wait a second. Do you need a schema for RLP too?
No, I think RLP is self-descriptive.
Okay. But yeah, used in Ethereum for basically making binary stuff.
Yeah. So yeah, we
Recursive
deserialized
linked
the first header.
Prefix.
Okay.
I guess actually I think the prefix part of it might be, I guess, the self-describing part where now I'm remembering it's like, if the thing is an array, then it's gonna like start with a prefix of like, 03 or something, that kind of deal. So it can tell
Right.
how long, like what the next thing it is in here and how many bytes to look forward before it has finished loading that very next thing.
Cool. So yeah. So basically the bridge client has to get the first header from which it starts. It has to be a canonical header. And this is a trusted thing that you probably should verify when you use a bridge. You need to check that the original header is legit. And it has to be part of the canonical Ethereum blockchain. Next, you get the hash out of the header, a number, and you construct a structure which you use to initialize. So best header hash indicates the last best header that we know. It's the highest proof of work header that is valid. And the highest means it has the maximum proof of work sum. So the proof of work is like a sum of all work in the past that is put into the linked list, or like into the linked list. So every next block references the previous block on which it's built and uses the proof of work of the previous block to create the new block. Now, some threshold for garbage collection given is how far we need to do the garbage collection, because we don't store full headers after a certain amount of time. Otherwise, we will grow too fast in terms of storage that the bridge consumes. So we collect, or we erase headers after some period from the head of the blockchain. Well, I guess tail, it doesn't matter. And so basically we'll just keep, for example, last 30,000 headers. If you need to prove something from the past for the header that was garbage collected, you have to provide this header potentially, or you can use this header when you give it to the prover. So you give the header, it can compute the hash of the header, and it will verify just the hash of the header in this chain. Now, finalized GC, so we say the chain is finalized, the canonical chain is finalized, and you cannot fork it from this given moment after this threshold is reached. This one will garbage collect all canonical headers from the chain. What kind of?
So this is for the client. Like the client is calculating the, like, what counts as final. Am I understanding that correctly? It seems like something that, like, I understand the bridge fairly well already. So for context for other people, like you have other kinds of connectors for sending fungible tokens or non-fungible tokens. And to me, I would think that we would want the what counts as final in Ethereum to live in different kinds of connectors. For NFTs, you might say, like, if there are 10 blocks on top of it, that's good enough. And for certain kinds of like other higher value tokens, you might want to say, we want to wait for 25 or even 100 blocks to be on top of it. So why does this live in the client and not in the connector?
So this one's saying that we believe, for example, that after 30 blocks, it's impossible to construct a fork from the past. So we say that you only need 30 blocks to, for example, to be able to construct a fork from any of these blocks. So how you prove that like a new chain becomes canonical? So you can have a fork, let's say 5 blocks in the past that builds 2 chains in parallel. So there's like active 51% attack going on, like, and then the canonical chain is the one with the maximum proof of work. But let's say the parallel chain that's going on is slightly less. So when it produces a new block at a given height, it will exceed the power of work, like the amount of work. But at the same time, your like previous canonical will also produce a block at this height, and now it exceeds the proof of work. So yeah, they can build in parallel until at some moment they run out of work, or like some chain wins. So we say in 30 blocks, it cannot happen anymore by this client. So like, yeah, so at some point we'll cut this chain out of the like canonical, and like we garbage collect blocks or headers that were like from the fork.
Okay, so that's just like core how you have to implement any Ethereum client, like client or no. You have to code in some GC threshold, basically, some measure of finality.
Well, you don't have to, but it's probably optimization, so you don't need to like keep them around after this.
I understand. Like I understand what it's for. I guess
happens.
I'm not asking why we have it. I'm asking why it lives here and not in the, like, why can't connectors specify their own finality concerns?
Well, they
Right?
can.
Like,
it's not
for this use case,
telling,
10 is enough. For this one, we want 30.
Yeah, we don't tell which is a final. We just tell after which we will not keep them. So like after 30 blocks, we will not keep the headers potentially.
So this is kind of the maximum.
And and like you'll need to like provide them again. I'm not sure if you can ever do this. So like once they finalize, I don't think you can fork it anymore, because it will reject the header that is so far behind as a like non-final and can be garbage collected. So you have canonical header hashes. So the given height, it will give the best header right now. It keeps all header hashes, which is a vector of all forks there at a given height. I think it can be abused if you like can mine so many blocks that are appropriate forks of a given block. Probably you cannot do this because you only store a hash here, so it shouldn't be an issue. But we use this vector when we do garbage collection for finalization. And we keep headers. So that's actual header from Ethereum that is given to us. Finally, infos. So info is interesting. Basically, it has a total difficulty, a parent hash, and a number. Number is like height. You need info if you want to compare two of them together. You don't need to like entire header to look at it. Just need the information for the given header. And finally, we have a trusted signer. So this is like for proof of authority testnet, apparently. Now what we do, we stick a canonical header hash. Then we add our new header hash at a given height. Then we use, we put the actual header into the list, and we create an info saying total difficulty is 0, parent hash is unknown, and this is the height like this. So that's an initialization. So we created a blockchain that we trust at a given height. This is our new genesis from which we will track entire chain. All right, so this is a view method that gives a merkle root at a given height. That's for validation. So if you want to validate it, that the block is, or the initialization is correct through a view call. This one gives the last block number using a infos and a best header hash. So best header hash is like our canonical best header with maximum proof of work. Now block hash for the given index, it actually gives you a hash from the canonical header hashes. So the idea is your last block number and a block hash should give you some type of finality. Here's a number of confirmations. So this is another one for safe, as you mentioned. So like for most of them, 25 is enough. And finalization is 500 blocks, so it's pretty far, quite safe. And you can use block hash safe. So you say, what is the canonical safe block that is 25 confirmations on top? So it has a chain that is built 25 valid headers on top. It also can give you
Which one is
all
last
known
block
header.
number using?
This is
it
from
the same
canonical.
one as block hash safe? Oh, it is. Okay.
It's not. It's a last on top. So like it's a tail, the best tail.
Okay.
Of the chain, like leaf. So blockchain is kind of DAG. So finally, the most interesting method is add a block header and how it works. So it again uses Borsch and also returns Borsch for some reason, because it doesn't return anything actually. We first get the header, we deserialize it. So this is a proof that the header, this is a proof from the DAG Merkle tree root. The header contains the epoch, so we know the epoch. And then we will be able to verify and compute eth hash efficiently using this proof. So we first deserialize. If it's a proof of work, then we verify that this is proof of work. If not, then we need to verify that the header is valid. So we find the previous header, a parent. We give current header, a parent, and the history to our method that runs verify header. And then we record this header on chain. So first, let's look at the verify header. So this is an inner method, so it's not exposed. It has header, the parent, and proof. We do Hashimoto Merkle. So this actual work that happens. We find the merkle root for the given epoch based on the header number. Then we hash the given header. We actually have it. Nonce, and then we go up the tree until we can reach the root, and the root should match. Or maybe we just return the root. So we have the hash that we computed, hash we computed, not the given hash from a given header. And we compare whether it's part of the difficulty that is set for this header. And we verify gas limits. We verify, so this is logic from Ethereum, the current configuration. So if Ethereum configuration gonna hard fork, we'll need to adjust this logic. That's why we need upgradability on this contract to be able to change this logic.
In simple question land, so what does a difficulty actually look like? I believe it's I'm guessing it's a very large number with a bunch of zeros, and then all ones, or how does that look exactly? It's okay if we don't want to answer this too, if we want to keep going
Yeah,
on,
so it's like just a bunch of zeros in front. So if you put it in a binary representation, then difficulty is number of zeros in front of the number.
So when it's like less difficult, more difficult, it's literally like one less zero, one more zero.
Question here is like, why are we using the header and not a previous header? If I just set a difficulty on my header to whatever I want.
But the difficulty is going to be like a number like 10 or 11. And that's going to say how many leading zeros the hash needs to have.
No, we like.
Did I understand that correctly?
This is completely broken logic. Like why we verify this, it's always true. What's going on here? It's kind of bug. So maybe we should follow up on this. It seems like some of this header should be actual pref, and we don't use it. I'm pretty sure this one should be pref, and this one should be pref, and maybe, yeah, this one should be actual header difficulty. But maybe also pref, because previous defines the difficulty that you need to do. And this should be a next difficulty. So that seems like a bug that you can right now abuse. Unless I'm missing something, because I can just specify a difficulty of 0 and mint a new header locally, and it will be valid.
You can submit stuff directly to this contract over and over, and like 51% attack Ethereum, or near the near client's representation of Ethereum.
The total difficulty will not be the correct one, because the canonical will have a higher difficulty than what my headers that I'll produce. But I can clearly break the contract logic by going very far in finality.
That's what I'm saying.
And
it seems like you can essentially 51% attack like this client's view of the world.
I can go and just produce 500 headers, and they will be considered canonical, so no one will be able to build on top of me plus I just need 25 to be considered.
And then you can start like sending your near address a whole
I
bunch of
can just
wrapped
like
dye.
mint whatever I want on like, yeah. Anyway, cool. All right, let's go back to now record.
Great attack.
Record header. Record header takes a valid block that we just verified. It's a through proof of authority or proof of work, and we update the canonical logic, do garbage collection, and all the stuff. So we update best info, compute. So for example, header is too old to be on canonical chain and stuff like this. We get parent again, then compute. We insert this header, compute new difficulty. And there's just a tiebreaker. Then we put it into canonical header hashes if it's actually canonical. And we do garbage collection on some old stuff. If it's not a canonical, we just record it because it means it's not a main canonical fork. And we don't garbage collect yet. So we only garbage collect old blocks when threshold is old. So this garbage collection, it basically goes on a given height and just kills all the like non-canonical blocks headers from storage. And for very old, we kill all of them, including the canonical one, but only keep the hash of the header. And I think that's it. So we have 14 minutes, so we can quickly look at the prover. If there's no questions on this contract.
I have a question, maybe generally, and it's okay if we don't want to go there. But I know that we've been talking about just kind of like generally the bridge. Like if the topic is kind of like the bridge, we've been talking about having an upgradable bridge for a little while now, and it seems like there's an issue there, and I'm curious, like if we know what is so tricky about that, or not.
So upgradable bridge, it basically need to handle a hard fork. We don't want a contract that like mintable to be able to switch manually. So you don't want to like, because you will not be able to unlock them on Ethereum side because or maybe you will be able, but it will require forking the fungible tokens and everything that depended on a canonical chain. But you probably don't want to do this. And the upgradability needs to be able to handle this hard fork to the new proposal once it exceeds like 51% or whatever the protocol threshold on Ethereum. Then it should switch to the new chain that is hard forked version. And we need to point all contracts to the new prover that will use the new client that is like a new version of the block. So it needs to seamlessly work after some point. So for example, a prover needs to just magically switch to the correct chain, because the hard fork on Ethereum is actually a new chain. Anyway, let's have this separately. So prover is actually not a large contract, but the way it works is it has a method called assert is client hash. So this can be used as standalone. So you just give a block number and expected block hash, and it calls save on a client side. So it gets the hash from the client side, so from the blockchain, canonical blockchain, and it verifies that it matches using inner method on block hash, which is just verifies that it's a callback to self, and then it compares them and returns true or panics. And the second is verify log entry. So this an upgrade. So you give log index, log entry data, receipt index, receipt data, header data, proof, skip, breach, call. Well, okay. Okay, so first what you do, you have a header, you verify locally from the header that a given log entry exists using a merkle proof from the root of receipts. Once you've done this, you need to call breach client to verify the given block is correct. And you can do this with this. It seems like this is just a little bit weird because the gas hash here is different, or like gas used here is different. So in theory, you can just call assert locally and return this promise. Finally, and this is just because our gas is very confusing, and we can replace it, I assume. It's like 100 teragas or something. 10 teragas, yeah, 10 teragas is enough, but you don't need this to be all the rest of the prepaid gas. It should be also like 5 teragas. Now, verified try proof is actually just technical implementation that verifies the Ethereum logic on your side. So prover is also fairly simple, nothing like complicated there. Also, I feel like there's another security issue is we don't verify the hash of the block. Or maybe it's verified in decode. Go ahead.
So one thing I learned, which was awesome, is the whole Boards serialization thing, and we need a schema for that. And we were looking at the init function, but then I think I probably missed it thinking about other things. But where was the schema for this?
For Boards?
Yes.
Or for,
yeah. So yeah.
So for this, it automatically constructed from this schema. So you give types here, so it's just a schema. So it's basically if you remove this part and then wrap it into a structure, then it's gonna be the schema.
Gotcha. Okay, thanks.
So yeah, so there's no problem with header hashing because hashing is done during the decoding. So you cannot really fake the hash. So yeah, so this one is fine. We only need to verify that the client logic is not, like, seems to be invalid. Any questions on these two contracts?
One of the last question I think I have is, you said earlier that some things are garbage collected, like headers are garbage collected, but if you need to go back, then you could say, oh, hey, here's a header, and it will be able to figure out the hash of that and complete it, basically. So does that mean that a minimal amount of the entire chain is saved, or is like everything garbage collected past a certain point?
No.
Okay.
It has hashes. It has historic hashes only. So it's always growing, but only by the size of the hash. So hash is like height, hash. Probably info is not garbage collected, so info is also there. So it's like reasonably large. So
Wow.
it has constant demand from the storage.
Gotcha, thanks.
Okay, I'll stop presenting and maybe some final questions and before we close.
I think we can call this one live security contract review.
Yeah, considering last two, that's true. Well, thanks everyone. Hope you enjoyed the session and learn more.